In this video, you will learn about the basics of refrigeration compressor. A refrigeration compressor is a mechanical device used to compress the refrigerant gas and increase its pressure and temperature so that maximum heat energy can be utilized. The key functions include suction of low pressure refrigerant gas from the evaporator and then compress it through compressors to raise its pressure and temperature, and finally discharge this high pressure gas to the condenser to release the heat. There are mainly two types of compressors: dynamic compressors and positive displacement compressors. While dynamic are further divided into ejector, radial, and axial type compressors, while positive displacement compressors are further divided into two categories: one, rotary compressors, and second, reciprocating compressors. Reciprocating compressors are further divided into trunk and crosshead type, while rotary compressors are further divided into vane, liquid ring, screw, or loop compressors. The working principle of a compressor is based on vapor compression cycle, or sometimes it is called vapor compression refrigeration cycle for the case of refrigeration compressors. It is a thermodynamic cycle used in refrigeration, air conditioning, and heat pump systems. The main components of VCC or VCRC are evaporator, compressor, condenser, and expansion valve. The performance measurement parameters of any compressors are capacity of a compressor, its suction pressure or temperature at the saturation level of the compressor. Second, the discharge temperature or the saturation pressure corresponding to that temperature. Refrigerant effect, which is the ratio of cooling capacity over refrigerant flow. Coefficient of performance, which is also called COP, and it is equal to refrigerant effect over shaft power, suction valve opening of a compressor, and the shaft power consumed by the compressor. These are the some typical parts of a compressor, of a reciprocating type compressor. It includes suction valve and discharge valve, suction strainers, and the relief valve. It also includes the complete oil circuits, which contains oil filter, oil charging and the drain valve, oil pump, and the strainer for the oil. The mainly temperature and the entropy diagram is considered for a compressor systems. And for the vapor compression refrigeration circuits, it is considered as an ideal case when we study the temperature entropy diagram. So what the temperature entropy diagram explains us that when a compressor works on a gas, it increase its temperature and also change the saturated vapor phase into superheated vapor phase. And when it passed through the condensers, it changed the phase from superheated back to saturated vapor and further up to the saturated liquid. And when this saturated liquid passed through the expansion device and after throttling, this saturated liquid converts into the mixtures of liquid and the gas. This liquid and the gas mixtures pass through the evaporator and it absorbs the heat from the space, from the surrounding, and then converts again into the saturated vapor, where this cycle again repeatedly occurs. Pressure and enthalpy diagram is considered for the actual cases of the VCRC. Previously, we have discussed the ideal cases where temperature and the entropy diagram is discussed, while for the actual cases, pressure and the enthalpy diagram is studied. What it shows that there are two zones of a complete VCRC system. One is the high pressure zone and other is the low pressure zone. So in the graph, the dome represents the change in phase. Under the dome, there is a liquid and the gas mixture, while the right of the dome, there is a superheated gas, and the left, there is a subcooled liquid, while the line shows right side saturated vapor and the left side saturated liquid. The top of this dome is CP, the critical point, where the saturated liquid becomes equal to saturated vapor, and which is the ideal case. In actual cases of VCRCs, there is also a flash vessel, and it is sometimes called economizer, used to increase the coefficient of performance of a compressor. If you follow this pressure enthalpy diagram, it reflects the two values from 1 to 3, and then 3 to 5, and then 3 to 6. In normal cases, in the previous slides, you have also reviewed that when the compressor start works, it changes the phase from point number 1 to 2, and then 2 to 3, and then back 3 to down 6, and 6 to 1. But when there is a flash vessel or the economizer present, then the economizer basically replace the vapors from the subcooled liquid after flashing, and these vapors contains the middle pressure, the pressure which is in between the high pressure and the low pressures, and the energy of these vapors in the form of enthalpy can be utilized as an intermediate stage for the compressor, and it increases the efficiency of a compressor. So if you see the curve on the right side, you will see that there is another point 7. So what the point 7 reflects, that point 7 reflects that the compressor overall efficiency has increased when there is a middle pressure streams come inside. So the change in enthalpy, total change in enthalpy will be equal to the actual case as enthalpy plus the ideal case. The standard codes which are followed for the engineering and the design purpose of a compressors are API 617 for the centrifugal compressors, 618 for reciprocating compressors, and 619 for rotary compressors. While for rating and thermodynamic performance testings, AHRI codes and ASHRAE codes are followed. For compressors, AHRI 540, and for the chillers 550 and 590 are followed. While for the safety compliance, ASHRAE 15, and for the refrigerant classifications, ASHRAE 34 codes are being used.